Okay, so this is May 2016. I'm going to do the first 10 questions. I'll do this in 10 question lots rather than all 40 in one go, which is a bit of a mammoth task. So May 2016, periodic table on the other side, and then they typically follow the order of the course, so it's calculations and then atomic structure, then periodicity, blah blah blah, and so on. So question 1, which equation represents sublimation? Now remember, sublimation is when a solid goes straight to a gas. So what we're looking for there is, now you might jump to iodine because you think, oh wait, iodine sublimes, but this is the reverse of sublimation. A gas directly to a solid is called deposition. So it's B, we've got a solid becoming a gas. It's just a physical change of state. It's not a chemical reaction like D. So B is the right answer, I hope. And then number 2, in which mixture is sodium hydroxide the limiting reagent? So all of these contain sodium hydroxide, which of course you get one hydroxide ion per sodium hydroxide. Sorry, a terrible shadow on there, but there's not much I can do. So it's reacting with sulfuric acid, which is a diprotic acid in this case. So if we maybe just fill those out a bit. So if we've got sodium hydroxide reacts with sulfuric acid. Now in this one, of course, we need a 2-to-1 ratio. So if we've got 0.2 moles of sodium hydroxide and 0.1 mole of sulfuric acid, well, in this particular case that's exactly the right amount to react with each other because we need double the number of moles. So it's not going to be that one because they're effectively, I suppose, both limited in some ways. In this one here we've got 0.1 moles of sodium hydroxide and we've got 0.1 moles of sulfuric acid. Now in this particular case, if we got 0.1 moles of sulfuric acid, we would actually need double the number of moles of sodium hydroxide. So if anything, the sulfuric acid is limiting in this one. So I don't think it's that one. Coming to this one, okay, now we've got a monoprotic acid. So sodium hydroxide reacts with one nitric acid, because you just get the one hydrogen per nitric acid. If we've got 0.2 moles of sodium hydroxide and 0.1 moles of nitric acid, well, here it's in excess. So it can't be this one, because they react in a 1-to-1 ratio. And in this one we've got 0.1 moles reacting with 0.1 moles. So again, this one does seem to make sense because we've got a 1-to-1 ratio. Let's go back and look at some of these previous options. So here we've got 0.1 moles. Sorry, it is this one, isn't it? That's the one we want to come back to. Because we've got 0.1 moles of sodium hydroxide, that could actually react with 0.05 moles because it's a 2-to-1 ratio. So this is the one which is the limiting reactant, because what we need there is we've got 0.1 moles of sodium hydroxide, then that would have to be 0.05 that it could react with. So if we've got 0.1 moles of sodium hydroxide, it's going to be limiting here, because if it's 0.1 we would need the 0.2. Should have grasped that a bit quicker. Number 3, why do gases deviate from the ideal gas law at high pressures? Well, molecules of a finite volume. I always find these quite tricky, these ideal gas law questions. I know there's to do with, basically the idea is that the molecules don't interact with each other and that there's no intermolecular forces if it's behaving as an ideal gas. So molecules of a finite volume, that could be a part of it, and that's like they do have to take up a certain amount of space. Cohesive forces increase the volume from the ideal. That doesn't make any sense to me, because you sort of think, well, if they'd stick together a bit, that would actually decrease the volume from the ideal, so I'm not going to go in with that one. Increase in pressure increases the temperature of the gas. Well, that is true, but I don't see why that would cause it to deviate from the ideal gas law, because if anything, giving the particles more energy would help to overcome any bonds between them. And then collisions between molecules occur more frequently as pressure increases. So let's think about that. Now again, that one does seem kind of reasonable, because if the particles are in a small amount of space, they're going to collide more often, and the more they collide, then you imagine that they might get these attractive forces between them. But you have to assume that the collisions are all elastic, and that basically there is kind of no change in energy when they collide with each other, so they just kind of bounce off each other again. So I'm not really convinced on this one, but as I say, I do find the gas law ones quite tricky to answer personally. So I'm going to go in with A as being my best bet, but I'm really not sure on that one. It could be D, but I'm thinking A. Number 4, which is correct for the chromium isotope. So it's 53, 24 chromium. So we've got 24, well, that's the number of protons, remember. and this is protons plus neutrons. So 24 neutrons, well that can't be right because it'd be 53, take away 24 would be the number of neutrons. So it could be either of these because it's an atom, so 24 protons. Similarly, it could have 24 electrons. And then, okay, how many neutrons have we actually got? Well, nucleons is protons plus neutrons. So we've got 53 nucleons. But how many neutrons is that? So neutrons equals 53 minus 24, which is 26, 29. Yeah, 29. So it's looking like this is the best bet then. So 24 protons and then 29 neutrons. As I said, nucleons is 53 nucleons because that's the protons plus the neutrons. Okay, number 5, which electronic configuration is correct for the selenide ion? So again, if we come and look at selenium, that's across down here. So that's going to be filling in 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then it's going to be the 3d10, and then we're across to selenide, and then it's the selenide ion, so it's gained 2 electrons. That's going to be out of focus. So that's going to be 4p6. So looking for the best match there, that's going to be, looks like this one, because it's certainly not the 4D, because yeah, the thing to watch out for is this, even though it seems to be in the 4th period, remember the D sub level kicks in the 3rd energy level. So this row here is actually the 3D sub level, just as the way this is the 4F sub level down here. So that's the one I'm going with. Again, they probably all add up to the same number, but it wouldn't be a bad idea just to check it. So selenium is 34. If it's a selenide ion, there'd be an extra 2 electrons, so it should come to 36. 2, 4, 10, 12, 18, 20, 30, 36. So that's right. But the others maybe will add up to 36 anyway, but it's just a quick check. Number 6, the diagram shows the first ionization energies of 4 consecutive elements in the periodic table. Which element is in group 14? So group 14 is kind of the same as group 4, remember. Now, this is one of these kind of tricky ones, but if you remember that sort of pattern in ionization energies, what I like to say is the old 2-3-3 formation. So if you kind of sketch off to the side, you get, it goes up 2, and then it goes down a bit and up 2, and then down a little bit and up 2 again. And remember, it's that kind of trend because you get a little bit of a dip there because you start taking an electron from a p sublevel rather than an s sublevel, and here you take it from a doubly occupied p orbital rather than a singly occupied orbital. So seeing where this matches into here, we can see it kind of matches in this kind of region around there, and then if this is 1, 2, 3 and 4, and then in 5, 6, 7, 8 or group 0, so that maps in quite nicely for B, I would say. So circle B, and you can see how that fits in that bit there. It's that little section, and then that's number 4, which would be group 14. Which element is a metalloid? Well, cobalt's a metal, so it's not that one. Arsenic, that's what I'm going to be going for. Cesium is one of the alkali metals. Yes, Einsteinium, that's in group F. Don't have any metalloids in group F that I'm aware of really, so we're going to go with arsenic. And arsenic's a good one to kind of choose because it's along that kind of little staircase that you have that separates the metals from the non-metals. So arsenic, what we're going in. Okay, number 8, which periodic trend is described correctly? So atomic radius, so increases going down the group, that's correct. Increases going left to right, well no it doesn't, because as nuclear charge increases then it pulls the electrons in more tightly, so that bit's wrong. Ionic radius going down the group top to bottom, decreases, well no, because it's going to get bigger. That's what always happens as you go down the group because you add an extra shell each time. Increases, well there's a bit of a funny one, ionic radius, because remember that's not clear cut because it depends on whether it's formed a cation or an anion, so you have to look at it on a case by case basis. So obviously on the left hand side the ionic radius kind of decreases as you go from something like Na plus to Mg2 plus to Al3 plus, because they're all isoelectronic, to 8, and then the bigger nuclear charge pulls the electrons in more tightly. But then when you come over to the other side, they don't lose electrons, they gain electrons, and then of course the ionic radius actually starts decreasing again. But you have a big jump in atomic radius ionic radius, because you don't get rid of that outer shell. So for example, the magnesium ion would have 2 shells, whereas the sulfide ion would have 3 shells. But the trend would be that the argon atom would be smaller than chloride, and chloride would be smaller than sulfide, because again, nuclear charge pulls those 18 electrons in more tightly. So, not that one. First ionization energy decreases going down the group. That is correct, because as the atoms get bigger, it becomes easier to remove an electron. However, it increases as you go from left to right, because bigger nuclear charge makes it harder to remove an electron. Electronegativity, the ability to attract a bonding pair of electrons. Well, remember, fluorine is the most electronegative element there is, top right. And so, yeah, electronegativity does decrease as you go down the group. As the atoms get bigger, it becomes harder to attract an electron. And then as the atoms get smaller, and you get your bigger nuclear charge, then the power to attract a bonding pair of electrons increases. So it's going to be D, electronegativity. Number 9, which does not affect the colour of the complex ion formed by a particular transition metal. So we've covered this recently in higher level periodicity. Oxidation state does affect it, whether it's a 2 plus or a 3 plus charge. Remember, a 3 plus charge pulls the ligands in more tightly and causes a bigger splitting. The number of ligands in the complex, well, that's going to affect it. Whether it's like a hexadentate or a sort of a tetradentate, sorry, not hexadentate. Yeah, no, something like a hexadentate ligand, or whether it's basically got 4 ligands bonding to it or 6 ligands to it, because then that affects whether it's a tetrahedral or an octahedral, and then that kind of affects the splitting, whether it's 3 on the bottom, 2 on the top as in octahedral, or 2 on the bottom, 3 on the top as in tetrahedral. So that is going to have an impact. Identity of ligands, well, that's what the spectrochemical series is for, where you get something like cyanide is sort of like causes a large splitting, whereas iodide causes a small splitting, so that is going to have an effect. Why did I put it across there? Yeah, it's not that. So it's basically this one. So the number of neutrons isn't going to have any impact, because they're just neutral neutrons. So whether it's got a couple of neutrons is not going to make any difference. That's the one we're going to go with. And then number 10, which best explains why transition metal complexes are coloured. So as electrons return to lower energy levels, light of a certain colour is emitted and the complementary colour is observed. Now they're trying to confuse you there with the flame tests of the alkaline metals. So we're not looking for that one. As electrons return to lower energy levels, light of a certain colour is emitted, so the complex appears to have the same colour. No, it's a bit of nonsense. Again, it's similar to that first answer. Remember, what we're looking for with the transition metals is they absorb a specific frequency of light to cause an electron to be promoted rather than it's falling back down again. So let's look at these. So as electrons are promoted to higher energy levels, light of a certain colour is absorbed and the complementary colour is observed. I like that one. That sounds like the right answer. And then as electrons are promoted to higher energy levels, light of a certain colour is absorbed, so the complex appears to the same colour? No. Remember, we have to use that colour wheel. So for example, copper sulfate solution is blue, but it's not because it absorbs blue light. The solution actually absorbs orange light, and we see the remaining colours, which then appear as blue, which is opposite orange on the complementary colour wheel. So we'll go with C. And that's video 1 done.